Good evening. On behalf of Engineers Australia, I'm delighted to welcome all to our Thought Leaders series, Facade Design, Brick and Terracotta Facades. My name is Amanda and I will be your host for tonight. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Brickworks Building Products. Brickworks is one of the world's largest and most diverse building material manufacturers. The company has built an enduring reputation and their customers are loved for their innovation, professionalism and dependable products and services. As Brickwork Building Products expands globally, they continually foster and advance their products and brand, continuing to lead the way through design, style innovation, sustainability and collaboration. With a broad product portfolio and manufacturing and sales facilities across Australia and North America, the company is uniquely placed to service the demands of the building industry. Please enjoy this short video from Brickworks.
Throughout the past 110 years, the face of building materials has continued to evolve. We're here for a lifetime of living. This is Brickworks. More than brick, and more than just building products, we are a foundation for today's lifestyle and a leader for today's style. We manufacture a wide range of building products. Products like no other. Local and international innovation, sourced from around the world to exceed customer expectations. Distinctive and luxurious products, beautiful products that stand the test of time. Building inspiration and innovation with an unmatched standing of style. This is Brickworks.
Today we will hear from two speakers, followed by a live audience Q&A session, and I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to welcome our first speaker for today, Grant Marr. Grant is the founding director of Jabin Group, a 100% Indigenous owned and managed engineering and construction services company. Grant holds the honour of being the inaugural chairman of the Indigenous Engineers Group, a chartered professional engineer, structural leadership and management, and fellow within Engineers Australia. Grant is also a proud descendant of the Gumbinga and Biripi nations of northern New South Wales. Grant has worked across a wide range of projects and disciplines within the engineering field with extensive experience in facades, ESD, design management, procurement and fabrication, gaining experience in both contracting and consulting roles, whilst working on local and international projects within government, aviation, defence, residential and commercial sectors. Further to his professional work, Grant helps to monitor young Indigenous engineers and hopes to develop the Indigenous Engineers Group into a group that provides support, networking and development opportunities for current and future Indigenous engineers. Please join me in welcoming Grant Marr.
Thanks, Amanda, for the introduction there, and good evening to everyone listening in tonight's webinar. I'm just here to give a bit of a brief talk through about various brick and terracotta facades, how we've gone to just give a preliminary design input and basically what they're used for. So I'll quickly run through about the application of brick and terracotta, and then have a bit of a discussion around sort of why the return of a modern brick and terracotta facade. Just a little bit of a chat around the system integration and some design. So, some structural systems with brickwork, how we've gone into the panelization and facade integration of brick and terracotta, and then have a little bit of a look at some features and specialist use of that material. And then I'll give some project examples. I've selected 4, 3 I've actually worked on, and 1 that you'll see it's quite an intriguing project. So when we talk about brick and terracotta, or when we think about it, we generally think of housing, low-rise boutique developments, and even education facilities. For example, here's a building at the UNSW, it's the electrical engineering building. It's done by Hassel Architects. I think it was around 2015-ish, something like that. But generally, it's sort of that sort of low to medium rise in housing developments. Obviously, we do have examples of high rise, but have a chat about that. So, commercially, pre-1970s, 1980s, within a long time actually, bricks and terracotta or variations thereof have been around for centuries, if not thousands of years, and they've been based on basically the reaction to climate and the requirements and need for shelter and also materials. Obviously early high rises used bricks, but generally, it's quite labor intensive. You had to use the materials around you. There was no real mass production. Obviously, that came into effect a little bit later in the century, where once we got into mass-produced terracotta and bricks, that they were used on high-rises. An example of a high-rise that uses these bricks is the Empire State Building in America. I think during my research, there's about 10 million bricks or so used on that particular building alone. Here we have a very early, the first picture I showed up is an old St. Vincent's College in Sydney. The second one you see there is like a red clay brick colour. That's the Bell Edison building in Birmingham. And then obviously we got the Empire State Building in New York. So then we moved into the 1990s, early 2000s, and we moved into kind of almost like a minimalist architectural design. There was also improvements and developments in materials to new mass-produced lightweight, also alternatives. We had improvements in glass technology. Became highly efficient, thermally efficient, in terms of providing high performance, high thermal performance. We looked at cladding. We had the development of fiber cement sheet, aluminium paneling, and obviously ACP. And then they were also looking at, because we're doing these high rises, looking at fast construction processes, efficient and cost saving alternatives to hand laying bricks. So here we got for example, we've got the MLC Centre in Sydney, which generally consisted of glazed facade and precast. And then another one, which is a huge development, is the Kens development, or the Westpac building in Kent Street. So you can see that's a fully glazed curtain wall system. So there was that kind of movement away from hand-laid brick or stone and into these efficient systems. Into the 2000s now, we're looking at a kind of a bit of a revitalization of sustainable elements, and we want to utilize sustainable materials on our projects. And coming from the earth, something that can be either reused, recycled, and it gives that sort of earthly feel to the building. Also, we've had the issues of combustibility. Lately we've had quite numerous examples of non-compliant cladding elements, which have proven quite deadly and catastrophic to the building industry. This is just one example, which was in Dubai. I believe it was actually called the Dubai Torch, and this is actually an ACP clad building where huge problems. Obviously we've got the Grenfell, and we've got the problems that we've had in Australia and currently going through at the moment. But we're also looking at putting the focus back onto the thermal performance of facades quite heavily and designing for the climate. Now thermally enhanced facades, they require to minimize obviously the overall building energy, and generally this is done through passive design. Using standard cladding systems, you have to team them up with quite a bit of cladding, insulation and development. So the cladding elements themselves aren't very thermally good. They don't perform very well. So we have to look at building those up, and they're just as an aesthetic. But moving on from that, we're kind of looking to also something unique. You know, the brick and terracotta gives quite a unique feel, quite an earthly and sort of almost like a homely feel to the building, and not so much like this monolithic structures that you see, solid glass or anything like that. And then as we've been developing it further, using bricks, we're kind of moving into new technologies where you're able to look at prefabrication and sort of material development, where it may not be just get that look, that brick or terracotta look, but there's other elements behind it, which allows efficiency and ease of install and control over fabrication. Brick also gives that, particularly with housing, it gives that look of or feel of like a strong, stable structure. I think that's why a lot of people go for it. Here's an example of a recent building. Unfortunately, I wasn't involved on it, but this is the Arc building by Crown. It was designed by Koichi Takata Architects, and this is actually the podium level part of a much taller building. And these utilize prefabricated elements and bricks into that to give it that look. Now, I'll just talk about a bit of system design and how brick and terracotta elements kind of get integrated into the facade. Obviously, we look at the primary structure, wall system, kind of like a double brick or a double cavity brick wall, where you have one element of the brick providing structural support, and then the other element of the brick or cladding, giving you the external rainscreen appearance. Obviously, then you got standalone rainscreen or cladding systems. This could be brick veneer or terracotta paneling or the like. And then you got feature or specialist applications, which may be solar shading or to that effect. So for the structural support, we have one example is a double brick wall. As I mentioned, you got the internal structural component, which may be either the clay brick or a concrete brick. The external veneer provides that sort of weatherproofing element, obviously in addition to internal sarking within the cavity to ensure the water, you don't get water penetration through, drainage, making sure flashings and drainage allow water to come out of that cavity. But generally this is done to give that sort of strong feel and a nice brick outlay. You see a lot of this on maybe that mid-rise, but it can be used obviously on high-rise buildings, which is quite heavy. You have to have the structural wall behind it with the brick veneer on the out front. You have to introduce movement joints obviously to the brick veneer, and the internal wall will generally span slab to slab with movements between each slab level. A typical R value for sort of an uninsulated double brick wall, you're looking in the order of R 1.3, 1.5 to that effect. Obviously, introducing insulation, deeper cavities, things like that, you'll improve your overall performance. But generally, that's kind of like a stock standard, installed product. Now, if we look into rainscreen cladding, brick veneers, we see these in housing a lot. Timber frame, insulated panel on the interior face. Gyprock cladding on the inside, painted. Then you have the brick veneer on the outside, which provides, not only protection from the elements, but does give a bit of a thermal break. The thing with bricks is they are quite thermally massive. They do hold heat, and they store heat. So the kind of you got to make sure that you insulate the internal surface. Otherwise, during the cooler periods, you will get re-radiation of that heat back into internal space. RVA is again, not going to go into too much depth, but you're sort of looking at R2 to R4, obviously depending on thickness of insulation, what you're using as a framing, cavity depths, similar things like that. Can do brick veneers obviously in high rise. Here you probably utilize, either structural steel, aluminium or light gauge steel framing, insulative, sarking build up, and then that face brick look, which, spanning over multiple stories, you'd have to introduce, movement joints and the like. Sort of a variable application here is also, to two different methodologies. You have the Insitu, where you're actually laying the bricks by hand, or nowadays we're seeing you can also move to a precast. So you're getting that sort of controlled environment fabrication of a brick wall set into a precast element and then brought to site and lifted into place. Obviously, that gives you a lot of efficiencies from an installation perspective, but also gives you control, whereas you're not relying on labour working around people on site. You can have that control in a factory and then bring it to site and install it. Then we move on to sort of, like a what do you call it? Maybe just a cladding, or a paneling system, similar to veneers, but this is where the introduction of, say, terracotta cladding would occur. You'd have a pre-constructed frame, potentially even a prefabricated panel, but not necessarily, and then you could bring it in and install it, similar to any other cladding system. We have various types of these cladding types. As mentioned, prefabricated wall panels. There's examples now of what's called a panel brick, and I think it's from Austral Bricks, where it gives you that appearance of a brick wall, but it's actually panelized in almost like a precast element, brought to site, lifted into place. So again, you have that control. Also, you have these brick-style clip-ins cladding system, which are almost like an individual cladding element onto a steel subframe and held in by clips. An example of this is the Corium product. You have direct or standalone cladding. These are, again, more on the terracotta side of things, and there's numerous examples of that. There's the Façade product, the Moding, which is German. Argentin, I think, is from Fairview, and then Faviton's another example, but there are obviously others to that, and that gives you basically a terracotta panel, extruded terracotta, bakes various colors, sort of that earthy color, supported by a subframe system, and then either bracketed back to concrete, steel, whatever the primary structure may be. Also, you can integrate this cladding into other systems, so into curtain walls or window walls, where you want to use maybe like a brick or a terracotta look into your spandrels. That can also be introduced, and I'll touch on that on an example later on. And some going outside of just cladding, bricks and terracotta especially can be used for specialist applications. Might be using for solar shading, sun shading, also just an aesthetic look, not really providing any other components of the building other than the appearance of it, or even a barrier, against impact or debris or the like. And I'll touch on 3 of these items in the project examples shortly. So here we got some projects. Obviously, this is a pretty famous one. Unfortunately, I didn't get to work on this project. When I was a contractor, we didn't win it, but I do know quite a few people who worked on this project. But it's a very interesting one where, even though it looks very complex, and it is, the methodology is still sticking to the very similar to pre-existing ways of supporting brick. Obviously, if you didn't notice, the Dr. Chow Chak Wing, which is the crumple paper bag, as they call it. So here's a kind of a architectural mock-up of what they wanted the brick to look like. So we've got that curve, sort of very sort of smooth curves into quite sharp curves as well, with glazed window systems within it. So if you look for sections through the building, see that basically the brick is held and supported by a structural steel frame, and then the bricks are panelized and then supported by that frame. So when I worked at AECOM, I was fortunate to have a chat with the people who designed and went through the whole process of doing this. And there was just a few examples of the mock-ups that they did and the process they did, but the basis of the support structure for the brick was brick and tie. So you still had the same concept of supporting your brick system with the ties. They just obviously had to be developed and designed in a way to take those stresses of, those huge big curves and sort of the looks like cantilevers sort of heading out, tying those bricks back into a solid steel structure that can be molded to the shape of what you need. The example of using terracotta and cladding for a solar shading element. Here's the advanced engineering building at University of Queensland. I was fortunate enough to work on the concept of this building back in 2011 when I was at Oricon at the time. I actually worked on the timber structure, but colleagues of mine got to work on the external solar shading and how to come up with the details. This is it was Kirk Architects and Hassel combination to do the architecture. And here we see that the terracotta is used actually as a solar shading to the internal space. So it's not a structural element, but it gives you that visual look. It's sort of like almost like a stone, an old stone wall or something to that effect. And then the modulation of the terracotta. So here was a concept, structural support of how we deal with and how we support the terracotta panels. And basically what it was done was a steel tube that was installed. They were done the same way, bracketed to structure. And then the terracotta was actually an extruded brick type of varying sizes. And then inside you could have basically a support element where you could rotate it and lock it into place to give you that different sizing. Here's some examples of the actual cross section of those terracotta panels, the extruded sizes, and they gave you the variability of being able to modulate the facade into basically any way you wanted to meet whatever the architect liked. It's just a quick sort of rundown of some architectural drawings. And this is the system mock-up that was done to show how you could move it around, position it into place, and basically what it would look like once it was installed on the project. This particular project I worked on, I helped develop it. It was I worked for Onsite Group at the time that we were doing the contractor, so we designed and fabricated and delivered the facade. And there's two particular projects that look exactly the same, but the construction methodology for the two is quite different. 5 Murray Rose was done as a curtain wall system, and 3 Murray Rose was done as a strip window wall, but with like a strong back. So they were fabricated at different times. So again, with the curtain wall systems, we looked at rather than having just a standard glass spandrel, the architect wanted to go for this visual look of banded. I'll just go back, sorry. Of a banded terracotta look. And I think in general, it was about 5 or 6 different colors that were used throughout the building of different sized panels. And then you got sort of the modulation across the facade. So these were extruded terracotta. I believe these were molding from memory. And each tile, 4 different variations of size. I think they range from about 100 mil up to 300 mil in width. Thickness was about 30 mil. And these were integrated into the actual spandrel. So rather than glass, we used terracotta. So this is an example of a section through that area where the curtain wall was prefabricated off-site. You had secondary framing, which is all factory controlled, so there was no installation of anything on site other than the finished panel. So that gave us control and also making sure that everything fit before it came to site. Obviously, working with natural products, they expand, contract with temperature. Cutting sizes can vary, things like that. So having that control within a factory setting allowed you to modify and change it if needed and control that. So here we see the final sort of section through that spandrel area. And obviously, gaskets and things like that were introduced to prevent this rattling around in the wind. That's just a close-up of a stacked, or to the bracket system, where it changes from, we also had glass, a combination of glass spandrel terracotta or full glass. So that's just an example of where we change from a glass spandrel to a terracotta spandrel with a small little projection. And then finally, this was the mullion. So this is a horizontal section through the mullion of the curtain wall, where we had brackets coming out, extruded, all custom extrusions, all custom done custom dies and everything. So this is all pre-done, pre-installed to the mullion, and then basically fitted together as we got to site in one big panel. So the final project I'll talk about today is in a current project that I've just finished designing, and it's in fabrication and will be getting installed on site soon. So this is the new Jackson on George bar area precinct in the new George Street Plaza. I think part of this project is a residential commercial high-rise, and then a bit of a plaza area which includes this, which is a new bar, retail and food and beverage. So this is aluminium extruded framing for the roof. So these are all sort of full, 11-meter high odd arches, aluminium extruded arches with a big hole cut in the ceiling. But the cladding that is put in there is all terracotta. So it's extruded terracotta baguettes, which is a circular shape with an internal sleeve for support. And these are basically, because of the variability of how the architect wanted this to look, they're actually installed individually. So these little snippets here are from a presentation that we gave. This just shows how these baguettes are actually installed onto the building. So on the structural aluminium section, which is the roof, it's holding nothing else but itself and the terracotta. So this is all bracketed on. So we have individual brackets for each baguette. Again, because of that variability, we had to do that because of the randomness that was desired. And then as we go through, we install each bracket, and then it's each little sort of supporting element. It's fixed off to the structure, and then it's panelized. Each baguette is then installed. And then that's the final sort of visual look that you hopefully see when we're all done. And that was just an example of the extrusion, the aluminium extrusion, which basically sleeves inside the terracotta baguette. So the baguette itself, or the terracotta component of the baguette itself, is not mechanically fixed, so to speak, in any way to the structure. It's sleeved onto the aluminium, and that aluminium has two end caps, which keeps the terracotta in place. And that end cap is then bracketed back to the structure via the extruded aluminium U-channels. And that is how it's all fixed off, and it's attempted to be a concealed fix. One thing on this project is, even though it's a feature, it is providing a little bit of shading, but mainly it was main design loads on this was a little bit of wind, obviously, but mainly impact loading. So we had to undertake both soft body and hard body testing, and that was for both human impact, so someone running into this, because it is a bar precinct. Even though there are glass barriers to the inside of this, so you can't physically run into it, it still had to be developed that, yes, it could take a particular amount of load, soft body and hard body load. And also the hard body was for something falling from a height, from maybe the residential buildings around it, that it would hit these baguettes and not fail. So, dislodge and fall to the ground, potentially hitting someone. So I'm just going to finish off showing a couple of little videos. they're in slow-mo, so just fortunately it just takes a little bit of time to see, but these are the two kind of variable densities that we tested for impact design for these elements. Obviously, one is the less dense, where the soft body may impact just one of those baguettes, and then the high density panel where you have quite a lot of them together, so it's distributed, or the load's distributed over them. So these tests were done under European standards, an IOTA standard, and also a CWCT a technical note, which is the if you don't know what CWCT is, it's a Centre for Window and Cladding Technology, and they're based over in the UK. So this is the test piece. This one, I'll just click it and see. This is the high density. So apologies for the delay, but basically the soft body is kind of like a big leather bag filled with glass balls or other kind of lead shot or something that affect a particular weight, and it's swung on a pendulum at a particular height to give you an energy. So here we see that because of the high density, it was able to take the high load and prevent, I think it barely even cracked when we tested it, and obviously no elements dislodged. So these high density areas were kind of focused more around areas where people were. And if we look at a low density, these were in areas sort of higher up the building, or also higher up on the roof, where we still could get a hard body, but less likely. And as I mentioned, these are based off of an IOTA, I guess the TR001 testing, which is the resistance of panels and paneling assemblies. So here we can see that it actually cracked and bent. Pieces of terracotta came off, but it didn't dislodge, it didn't completely fail, and it didn't fall off. So to the nth degree, yes, it partially failed structurally, but it passed the test because it didn't completely dislodge and fall off the building. So that concludes my presentation today. So I thank you for your time, and hope you found it useful. Thank you.
Thank you, Grant, for your insights. I'd now like to welcome our second and final speaker for this evening, Cathy Inglis. Cathy is an experienced materials engineer with over 20 years in the building industry and leads the innovation team in Brickwork's building products across brands including bricks, precast concrete, masonry, roof tiles and lightweight facades. Cathy has a Bachelor of Materials Science and a Master of Science. She is a specialist in her field and has worked at Brickworks for over 25 years in key leadership roles in management and business development. Cathy is on the National Board of the Housing Industry Association and represents the industry on several Australian standards, and was awarded a Member of the Order of Australia for services to the building and construction industry in 2020. Please join me in welcoming Cathy Inglis.
Thank you, Amanda. Good afternoon, everyone. Thanks for joining us today. Following on from Grant's presentation, I'm going to talk a little bit more detail into general facade design with brick and terracotta. This is specifically to look at aspects of AS 3700, the masonry code, but some in relation to testing on site, looking at complex masonry design and some project examples. The Australian standard governing masonry, which you'd all know, is AS 3700. The last edition of this is 2018. Sitting alongside the masonry code is the commentary, and this commentary provides lots of background information and some assistance with understanding the requirements of the standard. In addition to this, there's also AS 4773, which is masonry in small buildings. This standard is in two parts, part one for design and part two for construction. This standard is typically used for smaller buildings, mostly housing, but small size buildings that are governed by the design requirements of this document. So when designing for masonry, there's a lot of things need to be considered. Design for durability, fire resistance, serviceability, strength and stability. And when designing a masonry structure for strength and stability, you need to consider the loads as specified in AS 1170, the dead and live loads, the wind, snow and earthquake loads. But in addition to this, there are other things that need to be considered, and that's designed for resistance to water penetration, robustness and design for construction. There are other things also to be considered, acoustics, thermal performance as well. So this talk is too short to cover all of these. So I'm just going to look at a couple of specific things in relation to some project examples. Design for compression. When you get masonry units, the masonry suppliers supply you the F-UC, the characteristic unconfined compressive strength of the masonry. And the characteristic value is dependent on how many are tested to provide that value. The unconfined part of it depends on the height of the block, so it's all equaled out, so you can compare apples with apples and not dependent on the size of the product you're testing. AS 3700 then has a table which gives you the ability to calculate, depending on the type of unit you're using, whether it's clay, concrete or calcium silicate, what type of bedding, whether it's full or face shell, and what mortar you're using, to work out the strength of the masonry. So the strength of the masonry is determined from look-up numbers in this table based on the characteristic unconfined compressive strength of the unit and the mortar type, but also it takes into account KH, which is the relationship of the size of the brick to the size of the mortar. So the joint thickness factor depends on, as I said, the height of the brick to the height of the mortar. So if you have a typically 76 high brick, which is the common one, that is a KH factor of 1. So the calculation in the table is by 1. But as your brick gets bigger, the factor increases so that you've got more brick in the wall. The brick is the stronger part of the wall, so you'll get a higher overall masonry strength the less mortar you have in. As you go to smaller bricks, you have more mortar in the wall, therefore your masonry strength will be reduced by a factor. If you're looking for extra design for compression in your projects, if you're doing high load bearing capacity as required, you can use special masonry. And this is when you use special masonry and test it using Appendix C in AS 3700. So you make the samples with the same materials, so the same bricks, the same construction methods, the same mortar that you're going to use on site, and you make these samples to a height to width ratio with piers between 2 and 5 bricks high. They shouldn't be less than 3 courses, and then once you test them, you can see one being tested there. You then use Appendix B to determine the characteristic value for the strength. The design for flexural strength is another thing that you can actually test to get a better value when you're trying to push your design for masonry. So the characteristic flexural strength value is taken to be a value of not greater than 0.2 for clay bricks. If you want to get higher than that, you can test using Appendix D of AS 3700, where you test stack bonded piers. And there's 2 ways you can test them. You can test them by using the flexural strength by bond wrench testing or the beam test method. And you can see both there on the right. The schematic of the bond wrench test, this is where the top brick is wrenched away from the bottom, opening up the mortar joint and measuring the flexural strength of that mortar joint. Or you build a beam, as you can see below, with bricks joined end to end and mortared and applying a load across the beam. So either of those methods would work. The bond wrench test method could actually be done on site because they're actually can be a handheld machine, or you make the prisms on site and send them off to a lab for testing. So that's a way you can actually extend the capacity of your mortar by using special masonry, so testing on site, and that then is governed by your quality control on site, and the controls you have will govern how far you can push the design of your masonry. The 2018 edition of the Masonry Code also included stack bonded masonry for the first time. So this was following a series of research done at the University of Newcastle, a lot of testing to determine what the difference between stretcher bond masonry and stack bonded masonry. And the design rules that came out of this is that bed joint reinforcement needed to be included. And this horizontal reinforcement needed to be included and must be continuous between lateral supports, spaced vertically at centres not exceeding 6 times the thickness of the leaf of the masonry. It must be within 300 mil above and below a horizontal line of lateral support, and also in the first bed joint above and below any unrestrained horizontal edge of masonry, such as a window. And this is all detailed in a little simple diagram in the standard. So now we'll look at some project examples of masonry and some of the using those examples, how they can be built. So the Arc by Crown by Koichi Takada, this is built in Sydney, and it contains a series of arches built of brickwork to match in with the heritage context and the arches in the buildings nearby. So this building actually used no special shape bricks. It actually used all standard shapes. But at each slab level, there was a series of custom shelf angles used to support the brickwork, as you can see there. Barrack Place, which is just a few doors down from the Arc by Crown, this is another brick building that used a series of corbels above each window. But the tricky thing was this mega corbel at the grand entranceway to the building. So this design of this corbel, it had a concrete, the concrete support. The bricks here were all custom bricks. So there was 5 special custom bricks developed that actually had a centre rebate. And those centre rebates was a connector was used as a wall tie, essentially, to tie those back to the concrete. It also used a series of custom stitching rods and channels to support the brickwork. At the base of this corbel, you can see there in a bit more detail, it's probably easier to see than the previous drawing. You can see that there was the brick suspended from the soffit, and this was done by using stirrups to suspend the soldier course that was attached there. So you didn't see any of the steel supports, you actually only saw the bricks. And these custom angles that were developed and the stitching rods and the things were all done by Ancon, now called Leviat. We find that Ancon is really good. They have a whole series of standard ties and connectors for masonry, but they're also happy and willing to work on special projects to develop the necessary connections that are needed. And on the left there, you can see the series of custom bricks that were developed. These bricks had the centre rebate, and that's based on the bricks that were used for the UTS Geary project, the Frank Geary project at UTS, which used a similar centre rebate and tie-back system. The lower brick there, you can see on the lowest brick on that shelf angle is an L-shaped brick, and that L shape wraps around the front of the steel support, so it hides it in the brickwork. It's a clever way to disguise the steel and just see the bricks. So as far as bricks go, there's many, many shapes that are available. I don't know if you've ever looked at these, but I'm not going to go through all these. I'm just going to show you the extent of what there is available in solid bricks. So there's bullnose bricks, there's cants, there's squints and mitered bats, there's plinths, radial and transition bricks, sculptured bricks, and then finally there's custom bricks. So if this isn't one of the standard products that are available for what you need, there's a series of custom products that can be made. There are limitations on brickmaking, but we'll work with the architects and the engineers on their project to come up with something that can work, as we did on those projects that were just mentioned then. So now I'm going to take a bit of a leap and go and look at a project that's over in Korea. So this is the Celine headquarters that was built in Seoul, Korea. Now this project was built with bricks that were made by our partner in Italy, San Anselmo. So this project is the Celine flagship store, Seoul, South Korea. Architects were Caspar Mueller-Knier from London and Han Architecture from Seoul. The manufacturer of the bricks was San Anselmo from Italy, and the client is Louis Vuitton Moët Hennessy. So it's a 7-storey mixed-use building, and you can see there in the image it's got this beautiful veiled facade of brickwork with hit and miss, leaving out the bricks in certain spots. So for this project, this was built under the Korean building code. I'm not going to go too much into that, but working with the engineers over there, this building, the building height was 23 metres, the plan width was 13 metres, exposure B, it's an important factor of 1, and its wind speed was 30 metres per second. So from that, we worked out the positive and negative loads required for this brick facade and what restraints would be necessary to support the masonry with that open, veiled structure. So as I mentioned, the bricks were made at San Anselmo in Italy. The bricks were 500 long, they're 40 high and 100 mil deep. They're solid bricks. The brick itself is called a corso and it's got a wire drag on the face of it. The mortar thickness was a thicker than standard mortar joint. They did it at 20 mil thick to really make it stand out. That also facilitated some of the supports that are needed in the building. And it had flush mortar joints vertically, but rake joints horizontally. These bricks are handmade in Italy, where the brickmaker actually forms clots of clay, throws them into a wooden mould. It uses water and sand to create the shape, and then they use some wires to drag over the face to get that sort of rough textured finish. So the softness of this clay means it can't be an automated process, which is why they're handmade. They're hand stacked then onto drying shelves. They're dried, air dried, and they're eventually put in the kiln and fired at 1,000 degrees, like most other clay bricks are. So as I mentioned, the bond itself is a very open bond design. So this was a retrofitted facade that was supported 420 mil from the internal load for the existing load-bearing wall. So all the design considerations, there was local seismic regulations that required an L-shaped shelf angle to anchor at each story the brickwork back to the existing load-bearing wall. The steel rods were used vertically to connect the bricks, and these steel rods couldn't be seen through the bricks. They had to design it so you'd never see a steel rod. So that obviously needed a lot of careful analysis and a structural study done. So the brick production itself, there was 3 different lengths of bricks made and required to create this shape, a 500 mil, a 360 and a 220 long. There was 13 different brick types by the time it got finished with all the core holes that were necessary. And these bricks had a different combination. Some had 4 holes, some had 3 and some had 2. And these holes were positioned so that they could incorporate the steel rods without ever being seen, depending where the steel rods were. But each brick was imprinted with a code to identify its type and position. And you can see that on the top. That's in the mould box. You can see it engraved on the brick there. So each special piece was colour-coded to indicate its position in the facade. So the magenta, the teal and the lime green. So the magentas are the 500 mil long bricks, and they were made with 3 different core positions. There was a brick with 2 holes, one with 3 and one with 4. Then we've got the teal brick, which is the shorter one, the 360, had 2 and 3 holes, and then the smaller one only had the 2 holes. And as you can see there on the right, the whole facade was colour-coded so that they knew the exact position of every brick to be used. So you can see there a bit more detail about the different colours and the position of the bricks where they would sit. In addition to that, there was a special hanging detail. So at the bottom, you didn't see the shelf angles exposed. So there was a handmade special brick that sat on the stirrup system at the bottom to completely encase and protect the steel. So just looking at the facade itself, the veil and the amount of opening in the facade changes as you go up it. That's the one facade, and the other side obviously has a lot more openness at the top and the bottom. So it's a very unusual design, and it was a very intricate job for the bricklayers. So here you can see some of the brickwork as it's starting to go up. And you can see on the top left, the guy he's got his pattern with the colours, and he's actually placing the bricks as per the design. You can see the rods that are welded to the shelf angle, and these rods were actually only ever maximum 1.2 metres long. So to enable the threading of the bricks over the rods. You can imagine you couldn't do it floor to floor because it'd be too far to climb up, get the brick up and then drop it down the rod. So they were 1.2 metres high to facilitate the threading of the bricks over the rods, and then lift up, mortar them in, and then finish them off. So you can see it's starting to go up there. So it's very intricate brickwork. And that's the final image of the building. And as you can see, it's a sort of bit of a spectacular looking facade on the building. So just having a look at other steel, some of the really special, intricate designs of masonry really depends on the connectors, the ties, the reinforcement that's used to support it. Without going to really thick walls, masonry can only support so much under its own self-weight and self-compression. So when you get to these intricate designs, the use of reinforcing rods become very apparent and facilitate the designs. You can see here some twisted piers of brickwork. These actually have a rod that's threaded through the middle. Again, it was a brick that was made with a core hole to facilitate the position of the rod. And then that's tied back to, you can see the rear of the wall there with horizontal supports to take the loads on the wall. So now looking at a bit on terracotta, I just thought I'd cover off a terracotta breeze block. Our breeze blocks have sort of gained a bit of resurgence in the market. Traditionally concrete masonry ones were available, and probably you only saw them on your local council buildings, toilet block walls that let a bit of airflow through. But now they've sort of got a bit of a resurgence. So these terracotta breeze blocks are in the brickworks range. They're 290 by 290 by only 90 mil wide. So a very narrow block. And that narrowness actually really limits its capacity for the product. So to work out this, there's no real design constraints for this in the masonry code. We actually had to do a lot of testing to work out what the failure path would be. Because they want to be stack bonded, the pattern itself doesn't lend itself to be stretcher bond laid, but when you stack bond it. So we did a series of flexural strength tests. You can see there the schematic of it, and then also the testing that occurred up at Newcastle University. We built them 4 blocks high, 2 blocks wide, and applied the load and measured our mean flexural strength. So as I said, this is similar to the beam test I talked about before, slightly different because it's 2 blocks wide, but we ended up with a mean flexural strength of 0.65, so a bit more than what's allowed in the masonry code. So looking at these products itself, it's interesting. Architects really want big, huge walls, but they're very limited for their capacity because of the narrowness of the unit. They're very slender. So there I just show the difference between what you can do with it, the block laid in stretcher bond versus stack bond. And you can see that in stretcher bond, you can't build huge walls, but if you were at, I just use an example, I'm looking at a 0.5 kPa load, which would be your internal wind load, at 3 metres high, you can build a wall that's nearly 5 metres long. But if you look at it stack bonded, you can see how the capacity is reduced by moving away from the stretcher bond, which gives you a much better capacity of the wall. So with that and stack bonded, it obviously limits its application greatly. So we worked out, using reinforcement again, how we can actually make the walls so you can have bigger walls. So if you use a stack bonded, the breeze blocks, and you put a 1 block wide column at each edge, so that's a 90 mil block that's actually got 2 and 10 bars in it, it's reinforced, you then have a greater capacity and can build slightly bigger panels with these. If you look at that though, it's still not great. At 0.5 kPa, you can only go about, just over 1 metre high at 5 metres long, or if you want, it's only 1 metre wide, you can go 2 metres high. So they're not very big panels. So that's where the steel reinforcement comes in, and looking at using horizontal bed reinforcement. You can see there that with the one column either side, what the design of it would look like with the horizontal bed reinforcement as well. But instead of using a reinforced column, if you actually use a steel columns supported top and bottom with the horizontal bed reinforcement combination, that actually gives you much greater capacity for the wall. And at this point, you can get to if you look at the graphs there, there's the one on the left is for stack bonded with single skin with a steel plate stiffener. And now that you've got the steel plate stiffeners, you can actually get to a panel that at 5 metres long, it can be up to 2 metres high. So the steel obviously gives you greater capacity, which you all know. And then we also looked at these blocks because they get great shadowing potentially. You can lay them different ways. If you do a double skin, with the steel plate stiffener, you obviously get extra capacity because you've increased the wall depth, and you can see that. So it's going back to the masonry code and how we calculate things. This was just an example to say that we took what was in the masonry code. It was very limited designs. So we tested the flexural strength for stack bonding to work out our design charts, and then incorporate the use of reinforcement in the beds combined with vertical reinforcement bars to be able to increase the capacity of the design and use of these products. So there's a lot to do with the masonry code. I know there's a lot of engineers out there that aren't too familiar with it. So if you're not and you need some help with it, Think Brick, the Brick Industry Association, have a range of manuals, and these manuals cover each area of design. So up there you can see there's the clay masonry design for wind and earthquake. The next one's for fire resistance. The next one's for masonry and compression, and masonry for serviceability. There's also detailing and construction manuals, and manuals that give you the ability to calculate your spacing of control joints based on the E factor of the particular bricks you're going to use, so you can determine it rather than just working on the typical, standard 8 to 10 metres before you go to a control joint. You can work it out depending what bricks you have. So these manuals are really useful. And as always at Brickworks, we're happy to work with you on projects and the architects. If you need help with this, the manuals or information or specific products to meet what you're after. So that's always a good source of information. So I hope you've enjoyed seeing some masonry projects that are built with some great brickwork, combining great architects and great engineering on them. Thank you very much.
Thank you, and a huge thank you to our speakers this afternoon, Grant Marr and Kathy Inglis. It's now your turn to get involved. If you do have a question, could you please submit it through the YouTube chat box? If you'd like to leave your name, that would be lovely too. Thank you to everyone who put forward a question at the time of registration, and we might start with some of those. Grant, I might start with you. We've had a question that's coming from Giovanni in New South Wales asking, was poor design practice related to recent facade failures and collapses?
It's probably a good question. I'm probably going to take a punt and say it's in relation to the cladding issues that we've had. In a lot of them, they've actually been more related to the material use itself rather than the actual design or engineering of the supporting structure. Obviously, quite a few years ago, before the issue of the combustible facades and particularly ACP came on board, the structural design of those aspects was done, quite well, quite within standard, utilizing steel structure, aluminium, support framing and the like, and design for the relevant loading conditions, whether that be on a low-rise building or on a high-rise tower. So I don't think it was, yes, there was some issues with the frame in some buildings with, sometimes installation wasn't reflective of the design documentation that was done. But in a lot of cases, it came down to the material itself, and that's what created a lot of these problems. But that said, from experience in inspecting a few of these projects recently, then sometimes it actually came down to utilization of the wrong material. Maybe not having enough control on site of actually what's being installed. So the design engineering or design documentation having one particular document, but that being related once it was installed by the contractor, I want actually a good understanding of what should have been installed and sort of management of that whole process. That has been shown to be a reasonable portion of these issues as well. So hopefully that's answered a little bit of the question.
Thanks, Grant, for that. Over to you, Kathy. We've had a question coming from Razor in Victoria. Good evening to you, asking Kathy, can you please talk about your experience with perforated and patterned brick facades and half arches? Thank you.
Thanks, Amanda. Thanks for the question. I probably covered a fair bit of this in the presentation, but there's lots of examples at the moment of a variation of perforated facades, the patterning, protruding bricks, corbelling, combining soldier courses within the brickwork. There seems to be more and more examples of buildings where the architects are pushing the design to incorporate those features. So the ways to do them, as I discussed in the presentation, use a combination of shelf angles with ties, stitching rods, and various methods to connect the brickwork back to the frame of some sort. So whether it's a steel structural frame or a concrete structure, there's just a research the ways that can attach the brickwork, hold it back, and withstand the weight of the load.
Thanks, Kathy. And just staying with you for now, we've had a question that's come in it's a great question from Lana in New South Wales asking, Kathy, is there increase in demand for panelised brick construction? And if so, I'm keen to understand the cost benefits and carbon footprint compared between that and the conventional brick techniques. Thanks, Lana.
That's a very good question. And we're getting this every day. I think the push to move away from hand-laid bricks to precast and having the bricks cast in the precast, people can see the advantage of that because that removes the labour on site, maybe scaffolding, brick cleaning, waste disposal off-site. However, using bricks into prefabricated, whether it's into precasted or a prefabricated wall, is actually more expensive. It limits panel sizes with the weight limits of cranes, and it is more expensive. A single skin of brickwork, looking at the carbon footprint of it, if you're embedding bricks into precast, brick facings into precast, that will have probably a very similar carbon footprint for the same thickness. When you embed them into a precast panel, it's often thicker. Well, it will be thicker because you've got to include the reinforcement. So you've got the additional carbon footprint of the reinforcement and it being a thicker leaf of wall than what it would if it was a single skin of brickwork.
Thanks, Kathy. And Grant, we've had a question coming from Lawrence in Victoria. And Lawrence is asking you, what is the expected cost and construction time for these type of facades? Thanks, Lawrence.
Good question. There's a lot of variability. I can only speak on the projects that I've worked on, but where we've used, for example, the terracotta cladding, they haven't had that much of a premium over your standard, standard cladding systems. Obviously, there is a slight premium because you're paying for like a heavier product and sort of more, I suppose, workmanship goes into it. But in general, we've found that those particular facade systems are quite comparative to an extent. With some of the more, I suppose, featured and sort of architecturally complex facades, and yes, you do actually pay a little bit more of a premium for those. But again, there's not actually that much difference because if you can look at a solution, a simplification of the system, where on site you may be able to speed up the construction, that's where there's a considerable cost saving in that part. The material cost itself, yes, there may be a variance, but there's also ways that you, as I said, you look at ways that you can speed that up on site, whether it may be pre-panelization, but obviously there's limitations to it, as Kathy mentioned. But overall, having a good understanding of those costs at the beginning of the project and making sure that all parties are understanding of what is needed and is budgeted for, generally you can get that up front and it's actually put into the cost of the building. So, and what we've found is there's not as much variation as you would expect for these. To go into the nth degree, it's highly variable. It's very hard to say the exact price.
So can I just add to that, Grant, just to say that when you're looking at the cost, a lot of it goes back to the original way it's designed. When projects are coming to us now, it's often designed as hand-laid brickwork, traditionally laid, and they want to convert it to precast. It's way more difficult and more costly to convert a building if it's not designed to that method of construction to start with. So keep that one in mind when you're looking at your costs.
Thanks, Kathy. Thanks for jumping in there. And Grant, you mentioned about the combustible facades and how topical all of this is. And only this week at Engineers Australia, we've had 2 webinars around fire protection. So, Kathy, I just wanted to ask you, Hilton in South Australia is asking you, are brick and terracotta facades better suited to fire resistance compared with other alternatives? Thanks, Kathy.
Well, I think the first thing is they're all non-combustible, because when we make any terracotta products, whether it's a terracotta tile, a baguette, a louver, a brick, they're all non-combustible because we make them at over 1,000 degrees and the combustibility test is at 735. So they're all non-combustible. And it's really good news that they're actually going to be included in the NCC 2022 in the list of materials that are exempt from requiring certification or certificates to prove that they're non-combustible. So that's a good thing. As far as fire ratings go, the brick can contribute to the fire rating. Obviously, a 110 brick gets a 90 mil fire rating. So that will contribute that much to the external wall to add together with your other materials to get your overall fire rating of the wall. A terracotta cladding system like Façade and that, they're open rainscreen, so they don't contribute to the fire rating, but they're all non-combustible, so you can use them, but you just don't include those in your contribution to your fire resistance level.
Thanks, Kathy, and that's really good news about MCG. Grant, we've had a question come in regarding the terracotta spandrel, and the question is, regarding the terracotta spandrel and curtain wall, what precautions had to be made for the terracotta to remain engaged during transport? Typically, clipped terracotta tiles have gaps for thermal, etc. Thank you.
Yeah, great question. For these particular spandrels, we actually didn't use a standardized clip system. We had to actually design basically a custom extrusion to fit that purpose. What it was, it allowed, basically it clamped the terracotta in place, and these were actually at regular intervals, so they weren't just held in at the quarter points at each edge. We had them quite regularly spaced out. I think it was about 50 to 100 mil spacing, 100 mil spacing at the most. So they were actually clamped in quite considerably. They had pressure gaskets on them as well. So the way you had to install the terracotta was a row at a time. So that's that was the trade-off by using terracotta in the facade system, is that even though you've got 5 or 6 layers of terracotta, to be able to have that rigidity and that sort of stability of the panel, is that they had to be installed from the lower panel up, and then obviously when you replace a panel, you've got to bring the lower panel down. So that's why we had a lot of breaks in the system, where even though we might have had a 2 meter high spandrel in some locations on this particular project, the standard spandrel was only 900 mil. But where we had to say a larger spandrel, we actually had breaks in the system where we had maybe a little feature strip, so you didn't have to start pulling off 2 meters high of terracotta. It was sort of limited to only about 900 mil. So in terms of transportation, those gaskets allowed quite a bit of movement in them. So obviously that takes care of a lot of thermal, because where these were fabricated overseas, you're going to have temperature fluctuations. So we had to make sure that those temperature fluctuations are incorporated into the design. Obviously, when you're on site, or when they're in final installation position, you're going to have the solar energy hitting these things up and ambient temperature. So there was also the effect of making sure that your temperature ranges that you were dealing with, there was allowed enough expansion and contraction there. During transport, we had special rigs made up to store them. So when they went into the containers to be shipped to Australia, We didn't just have them stacked really close together like you do with normal curtain wall systems. We actually had a bit of a space. I think we had an additional 150 mil, which actually reduced the amount that we could ship, but we needed to do that to ensure that we minimize the risk of breaking to that terracotta. Even though we had the glasses, in this particular case, glass was a lot easier to replace than terracotta because that terracotta was coming from Germany, so we had to be careful. So yeah, to try and deal with that, we tried to mitigate or minimize the risk as much as possible for any impact. The tie downs of the curtain wall systems on the rigs when they were shipped, making sure that the gaskets had enough flex that you weren't putting too much pressure on the terracotta, but you're also having enough to allow not too much movement around, bouncing around. So we really tried to eliminate any metal to terracotta connection. We tried to incorporate gaskets where we could, rubber gaskets to minimize that. So we looked at sort of all those options and we actually came up with risks and how we would mitigate those risks. And that actually went into the design as well of how the final installation. Hopefully that's answered a little bit.
Thanks, Grant. And obviously transportation is a big issue. Kathy, do you want to comment from a manufacturing point of view?
Transportation of products is always critical to them arriving on site still looking good. We did some Façade projects where the tiles were sent to Thailand. They were fabricated onto curtain wall structure, put in a container and sent back to Australia, and they went on the building at University of New South Wales. University of Sydney, wrong university. And in that there was they broke one tile in the whole shipment and there was probably a couple of thousand tiles in that prefabrication part. So as long as they're packaged correctly, then the transport will be fine. But again, you try and avoid the metal to terracotta part in the packaging and have something between them.
Thanks, Kathy. And over to Isaac. Isaac's put in a question around safety. It's a great question. He's directed it to you, Grant, asking, in the first instance, how is safety in design managed with regards to post-breakage dislodgement of the spandrel panel terracotta panels or shading protections? Thanks, Grant.
Yeah, it is a good question, and being the material it is, we try to incorporate that very early on. So rather than an afterthought, the safety aspect of this was taken very, very highly because of where it was. It was the spandrel installation was actually around Sydney Olympic Park. So there's a lot of people walking around, so you're always worried about dislodgement of elements from your facade. How do you mitigate that? Where we came into play with the terracotta, obviously we did a full scale of testing. So not just the nominal, silhouette testing, which is your water and your wind loads. We also did impact testing on them to determine what level of impact, and that was based on also maintenance loading. So when we had rope access people, that they weren't just going to bang into it and it breaks and it falls out and dislodges. Another way that we incorporated that sort of safety element in was those clips that I mentioned before. Although these 30 mil thick extruded terracotta bricks could easily span the 1500 mil, which is the panel width. If we only supported them on the edges, they could actually span that from a strength point of view. However, for post breakage, we needed to ensure that the panel didn't dislodge. So that's why we had these additional clips in at every 100 mil. So if the brick did fail, the terracotta did fail, there was a significant amount of support there to prevent that dislodgement of the panel. Obviously, with the incorporation of the gaskets as well, you're minimizing that sort of connection to hard materials, say metals and aluminiums and things like that. So you're allowing also a little bit of flex within the system. If there is an impact, you're not hitting terracotta directly onto metal. You're allowing a little bit of gasket flex. You're giving a little bit of compression. So that is where that component. Also, where the terracotta spandrels was situated, under every single terracotta panel was a projection, and that varied between 250 mil to 600 mil. So you also had a break and a little bit of a horizontal projection, whereby if anything actually did dislodge, it would actually fall onto that projection first before it would hit the ground. And that was also incorporated into the design of the building for those to be used as solar shading. It just happened to be that we also looked at using that as that sort of failure mechanism as well as a over and above component for that. For those other shading elements with particularly I think it was with the advanced engineering building, thinking back to that, because those were actually installed in locations where it was actually a slab projection out, so these weren't hanging directly off the building. Directly underneath those solar shades was actually a slab projection out from the main facade. So if there was any potential of dislodgement, it would actually fall onto that horizontal area where there was no access or very minimal access. It wasn't any pedestrian access to it all. They also undertook some level of impact testing from memory. So it had to meet obviously your maintenance load impacting, but also an additional impact load. But as I said, the safety element you incorporate into the design well before you even think about getting to site and then trying to solve it. You looked at it very well and was okay, well, if this was to dislodge, what's going to happen? Or if it was to crack, how do we hold that in place for a period of time that we can actually get there to replace the system? That's how we did those for those two jobs.
Thank you. And Kathy, a question for you from Pack asking, is there any method for getting compressive strands for brick on edge?
Yes, you just have ask for it to be tested. So it's not obviously the direction we normally test the bricks in, but it can certainly be done, and just ask the supplier to provide the testing for the specific brick you need, and it can be done.
Thanks, Kathy. Grant, Peter is asking you a question, asking why was terracotta used for the baguettes? Was it for aesthetic reasons that it appears to be a higher risk for brittle fracture, even though thorough testing was done? Grant.
I'm assuming it's the Jackson and George project. That's where the baguettes were used. But yeah, good question. We actually offered up a alternative solution for that. However, the material appearance, the look, and the color was very specific to the project. The architect and the client, that's what they wanted. So they actually wanted to use terracotta because of that look, the color, the feel, that kind of thing. Yes, the brittleness of the terracotta was a concern, and that's why we tried to undertake as much testing and sort of research as we could. Coming from the supply side of things, we tried to look at terracotta, strength design for that. But at the end of the day, we had to undertake as much testing as we possibly could. The test that you saw there, that was only one of about 10 I think we ended up doing on each project. So short answer, we tried an alternative. We offered the alternative because of that, looking to move away from that just for that particular idea. That came from obviously the contractor was looking at that as an alternative solution. But at the end of the day, the terracotta gives you that look that you can't get with aluminium. And so we went down the road with the client and with the design team to develop that.
Thank you, Grant. Kathy, we've had a really great question from Hilton asking you, Kathy, would a building such as Celine be a once-off with increased costs for aesthetic reasons?
They are a once-off, but often when the moulds for a handmade brick or a custom brick are made, then that's already there. So that is the cost that goes in to make custom bricks. We have a mould cost. And I think a good example of that was here, the brick dies that were made for the Geary building, UTS, they're now in our range of products, and some of those were used for the Barrack Street project to make bricks for that. So if you happen to pick a shape that someone's already used, then there's no extra mould cost. But if it's one you want specially that's never been made before, there is that upfront cost that goes into the project.
Thank you. Thanks for that. And just staying with you, Kathy, Anika has asked a question to you. Noting the climate active poster behind you, Kathy, what are the climate impacts of brick versus other materials? And do you have available EPDs and carbon amounts for the life cycle of typical units? Thank you, Anika.
Yeah, it's a good question, and yeah, it's very relevant at the moment. Brickworks actually have a fully carbon neutral brick that's certified under the Climate Active program, and we've had that since 2014. So that's a whole range out of Tasmania. And only recently, about 3 months ago, we got our second Climate Active licence, which is for any brick or paver manufactured in any of our 11 factories around Australia. And so that's so you can pick a local product for a sustainable project and get Climate Active for that quantity of product going to that project. To do that, we've had to demonstrate that we've reduced our emissions significantly over the years, that we've done the full EPDs and the life cycle assessment, and that's all in a public disclosure statement, which we have to publish to get our Climate Active licence. So that's all available. And so I'm just going to add, there was a bit in there I forgot about the comparison to other materials. So bricks do have high embodied energy as we manufacture them. As Brickworks, we've reduced our our emissions, CO2 equivalents, by 45% since 2005. And so that's a significant amount over the years. We've now got a strategy to work towards the next 2025 and what we're doing, and then towards net zero 2050 as well. So compared to other products, I always look at it and say there is that embodied energy in manufacturing them. But when you look at them over the life of the project and the life of the product, with virtually no maintenance, we give a 100-year warranty, so you've got over 100 years of life if your building lasts that long. The energy can actually be very comparable over the life cycle of the building.
Thanks, Kathy, and that's wonderful to hear. And we're coming towards the end of our session. As always, the time goes very quickly. But, we're seeing a lot more brick facades projects around Australia than what we did a few years ago. It's very popular, had a resurgence. On behalf of Engineers Australia, for our young engineers that are coming through, what sort of advice would you have for them who are looking to know more about this or enter into this field? Grant, as a facade engineer.
That's a really good question. Yeah, it's becoming a resurgence really in terms of the facade design. It's becoming a very specialized field, and basically, obviously, coming from where I came from, a structural background, so having an understanding of structural systems is a big benefit. But understanding the sustainability side of facades and the materials and sort of looking into how you can use materials in different ways, and pushing for and you're in a position where you can try and push designs down the road of that sustainable initiative, which I think is a very important part. For young engineers coming up, I would think that sort of looking into facades is a fantastic area because you get to do such a variability of work. You're not just tied to one material. Look at this. We get to work with brick, steel, aluminium, glass, stone, everything. So that's what I really love about this particular area of engineering is that you've got that huge variability and you get to work with a lot of different materials. So broadening your scope of work, not just sort of focusing on one particular material, but having a look at how you can incorporate different materials in your facade, how they interact together. Again, having a look into how actual sustainable these are, who are they coming from, where are they coming from, having an understanding of that as well as the engineering, the pure design, the pure engineering side of things, I think is really critical into your understanding of the facade, and I think that's how you'll go quite a long way, and get quite respectful in the industry is sort of having that knowledge about those materials. So yeah, I think that was advice given to me, when I was first starting out on this, was not try and be sort of dictated by one particular design. Really starting to broaden and research into different areas. So.
Thanks, Grant. That's great advice. Thank you. Kathy, do you want to make some closing remarks around maybe just not for our future engineers, but from a manufacturing perspective, future trends as well?
Yeah, so a future engineer, we'd love to have more facade engineers out there that understand masonry design. There's so many architects that are pushing bricks and clay products to the limit at the moment, and we sort of provide that conduit between the architect and the engineer with the brick component and manufacturing the bricks. We work very closely with, as I mentioned in one of the buildings, like Ancon, that have or Leviat now, sorry, I keep forgetting they've changed their name, working with them closely on the hanging systems to work with the bricks we design. So we're always happy to help on that, and we know that architects are using brick more and more because they want the honesty of the material, the durability, the low maintenance, and I think they know there's no great concern with fire and combustibility issues, so that's part of it. So from a manufacturing point of view, it's always exciting. Part of my role is designing new products and developing building systems. We've always got new things on the go, so keep your eyes open for those. And incorporating, as Grant said, looking at new materials, new designs, new ways to use things in a more sustainable way. That's always a great thing. And, come to us with ideas and thoughts, because we always love to hear those so we can continue to develop new products. But our biggest push as manufacturers at the moment is to work towards net zero, and how we do that. We're a large manufacturer. We've got 29 manufacturing plants in Australia. So we've gone so far to now, but we've got a long way to go. And that's going to change, making our products more sustainably, lowering the carbon footprint, but also making the products have a sustainable application for when they're used in the field. Thanks, Amanda.
Thanks, Kathy. Yeah, and that's great. As you can, we've just come off the Engineers Australia Climate Smart Conference, and it's wonderful to hear that messaging being supported around different sectors. As always, we've run out of time, and it's all we have time for today. Please join me in thanking Grant Maher and Kathy Inglis for taking time today to share insights and their knowledge. I'd also like to thank Engineers Australia's industry partner, Brickwork Building Products, for making our webinar possible. And to see more in the series, follow the link in the description box. As always, we're looking for feedback on today's session, help us improve and plan future programs. So if you could, just take a couple of minutes to complete a short feedback form, which is linked in the description box below. Thank you again for joining us, and we look forward to welcome you to a future Thought Leaders webinar. Thank you and good evening.